All right, so today we're talking about the history of the atom, which is targets 3.2 and 3.3. So, the first person that we need to talk about is Democritus. Now, Democritus lived in 4th century in Greece. Now, remember, 4th century is like, the year 400 or between 300 and 400. And he was a philosopher, which are guys that generally came up with all sorts of great ideas and kind of thoughts. And one of his thoughts was if you take something like a rock and you split it in half, and then you keep splitting it in half over and over and over and over again, eventually you're going to get to a spot where you can't divide it any further. So his thought was that matter is composed of small, indivisible, and indestructible basic units, which are called atoms. Now, with this, there were a couple problems. First, it lacked all experimental support. And the second problem, which, kind of ties into the first one, is that he didn't test his theories because of a lack of technology. But overall, this is a guy that gets credit for coining the term atoms. Now, years later, like 1500 years later, an English school teacher named John Dalton came along, and he developed what we call the atomic theory in 1803. Now, in his atomic theory, there were 4 main parts. The first one is that all matter is made of atoms, and these atoms are indivisible and indestructible. Now, that probably sounds a little familiar, right? Now, the next one is that all atoms of a given element are identical in their mass and properties, meaning he's saying that every single hydrogen atom is exactly the same, or every single carbon atom is exactly the same. Now, his third point was that compounds are formed by a combination of 2 or more different kinds of atoms. And then finally, his fourth point to the atomic theory is that a chemical reaction is just a rearrangement of atoms. Now, overall, this is a pretty darn good theory, and some of these points still hold true today. But let's talk about some of the problems with his initial theory. The first one was that atoms are not indivisible and indestructible, meaning we do have the ability to divide atoms into smaller parts. And in fact, if it helps, some of you guys maybe learned about this in middle school. This is where we get what we're thinking are quarks, which are the things that make up protons, neutrons, and electrons. Now, other than this, the other big thing that is a problem with this theory is that atoms of the same element are not identical. Now, in terms of properties, they can be, but one of the ways that they're different is through the mass. And this is what we refer to as isotopes. Now, we'll talk more about isotopes later on in the unit, but that's just one of the ways where atoms of the same kind, like a single sodium atom, or sodium atoms rather, are not all exactly the same because they have slightly different masses. And we'll talk about that later on. Otherwise, in terms of Dalton's model of the atom, because he had a very basic understanding, he pictured atoms as kind of these just generic sphere shapes. And so with this, if it helps, if you think to what we did for our modeling matter activity last unit, that actually kind of goes into some of the basic ideas of atoms, where we just use simple shapes to represent atoms. Now, after John Dalton, the next guy that came along that furthered our understanding of the atom was J.J. Thomson. Now, J.J. Thomson was an English physicist who was studying electric current. Now, while he was studying electric current, he performed what's called the cathode ray tube experiment. Now, in this experiment, which we'll talk about in a second, he proved that any element can emit these negative particles, and all atoms actually contain these negative particles, which he called electrons. And so let's talk about the way that the cathode ray tube experiment actually works. And so the idea is you have this glass tube, which is known as your cathode ray tube, and then you essentially turn it into a vacuum, meaning you suck all of the air out of this. So there's very little or no air within this glass tube. Then you apply a current or electricity to each side of that tube. And what happens is one of the sides gets really, really charged, so this negative charge, and then the other side gets this positive charge. Now, the reason that this happens is when you hook this up to electricity, electricity then was direct current, meaning one side was considered the positive side, which is represented by the bigger lines, and one side is the negative side, which is the smaller lines. So what that means is electricity flows from, we say the positive side to the negative side. And in reality, what that means is this negative side here gets this huge buildup of negative charge. Now, when we have all these negative charges, eventually, because they're repelling each other, some of those negative charges shoot across and make their way to the other side. And then obviously they can continue through the circuit here all the way back to the high voltage generator where they repeat the process. Now, in reality, this at the time was a very, very complex experiment, but believe it or not, years later, like just under 150 to 200 years later, everybody ended up having one of these actually in their house because the cathode ray tube is actually an original CRTV. So if you guys ever have, or ever had one of those big TVs, so not a flat screen TV that's super thin, but one of the bigger TVs that's longer in the back, it had this cathode ray tube in it. And then what they were able to do was shoot these electrons at the screen. So in the back of the TV is this cathode, or the negative side, and then in the front, where your screen is, where you see the picture, that was the anode. And then they'd shoot electrons at the TV. So if you guys have, like an old TV at like your grandparents' house or something like that, where is this CRT TV, maybe you guys have noticed that after it's on for a few minutes, if you walk by, you can actually get shocked a little bit from getting too close to the screen. And that's what this is it's this cathode ray tube that's shooting these electrons or these negative charges at the screen. Anyways, so enough about the cathode ray tube and TVs, and let's talk about his model after he kind of went through this experiment. And so for Thomson's model of the atom, he had kind of built on the original model by John Dalton, so a spherical shape. And then he said that it's this positively charged dough that has these negative charges kind of embedded within it. Now, remember, the reason that he's saying that the dough is positive is because he determined that there were these negative charges. And he's like, okay, well, if there's all these negative charges and they're repelling each other, there has to be something that keeps them there originally, which is how he got this idea of a positively charged dough. Now, overall, this became known as the plum pudding model. And so anytime you hear the plum pudding model, this is the exact version of the atom that it's referring to. Now, after kind of Thomson's model of the atom came through, the next guy was Ernest Rutherford. And he was actually a physicist that worked with J.J. Thomson in his lab. Now, the big thing here is that Ernest Rutherford worked with alpha particles. Now, alpha particles are positively charged particles, and they're about 7,500 times larger than the electron. So much, much bigger. Still tiny, compared to you and I, but much, much bigger than an electron. And he performed what is known as the gold foil experiment, where basically he just set up a energy source and he just fired these alpha particles at a piece of gold foil. And so let's talk a little bit more about his experiment. And so he set up this alpha particle emitter, which was essentially a piece of lead that, essentially was a simple X-ray. and he would shoot these beams or these alpha beams through here. Now, with the gold foil there, he noticed that most of the alpha particles ended up just going straight through. Now, every once in a while, some of the particles he noticed would be going through, they'd end up going, or as they're passing through the gold foil, they would deflect at an angle. And so when it goes through, it hits something and then deflects. And then finally, the last thing was that some of the particles ended up reflecting straight backwards. And so this is where he's like, how come most of the particles go through, but every now and then something happens and they get deflected? And so this is where he started thinking, and he made an inference. And his inference explained why these particles got deflected. And it was that there had to be a very small positively charged thing in the middle of your atom. And so with this is where we actually get the discovery of the nucleus. And so this, then, after he's kind of saying it's really, really small, and remember the reason he's saying it's small is because most of those particles went straight through the gold foil. So if most of them go through, that means that they're not colliding with that nucleus very often, which is why he's saying that it's very small, but he kept with the idea that it has to be a positively charged thing. Now, with the gold foil experiment, this developed his model of the atom, which I kind of like to refer to as like the Jimmy Neutron logo, for those of you guys that watched Jimmy Neutron as kids. And so with this kind of version, he said that there's the nucleus in the center that has a positive charge, and then there's electrons surrounding the nucleus. And so those are the electrons surrounding the nucleus that are kind of floating around in these rings. And ironically enough, I didn't even realize it, but there's another version of it. And so with Rutherford's model, that's kind of the big change here, is that he decided or realized that instead of the nucleus being this really big thing, it was this really, really tiny thing. And then Niels Bohr came along. Now, Niels Bohr was a Danish physicist, and he also conducted different experiments with electric current. Now, in his experiment, one of the things that he kind of did that was a little bit different, and it was kind of with the cathode ray tube, or built on the cathode ray tube, is that as light was passed through a prism, it ends up splitting into distinct lines. So you remember how earlier we were talking about with the cathode ray tube, there was these electrons. Now the electrons do give off this kind of form of light, and different elements appear in different colors. Now the reason for that we'll talk about later on in the school year, but that those different shades of light, or those different colors of light, when they're passed through a prism, they split. And what he saw was that each element has this very distinctive set of lines. So if you guys, can picture light going through a prism, the light goes in and then it splits into like the rainbow color. So same idea, except instead of it being the full rainbow, you only get certain colors. Now with this, Niels Bohr was thinking, and he came up with the inference that all of these electrons have to orbit the nucleus in these distinct energy levels. And his idea was, because if each element gives off different, sources of light, or their kind of prism beam after it's separated is a little bit different, then the electrons themselves have to be in different places. And so with this, he gets credited for the discovery of the energy levels of an atom. And so Niels Bohr model of the atom is probably actually pretty similar to what you guys have maybe seen in the past with biology, or just with what you initially pictured the model of an atom looking like. And so here, the big thing is that there's the nucleus in the center, and then surrounding the nucleus, we have these elements that are orbiting the nucleus in what we call defined energy levels. So each of the energy levels is represented by one of these rings. And so the idea is the electrons are only on one of those rings. And then as you add more and more electrons, you add more and more kind of dots to your rings, as well as extra rings past, just this third one here. Now with this, and kind of going along, kind of much more currently, the last scientist, or the last big scientist that we're going to talk about, is James Chadwick. And with James Chadwick, he figured out that all of the masses of all atoms except for hydrogen were known to be different than the combined masses of their electrons and their protons. Now, okay, well, if there's a mass that's different than the combined mass of the electron and the mass of a proton, and the way that they kind of figure this out is through their previous experiments. And for what it's worth, they figured out that the proton, much later on, was actually an alpha particle. So earlier, when we were talking about the gold foil experiment, and alpha particles, those are also known as protons. So they were able to find the masses of these things, but they realized that it doesn't add up to be the mass of that actual element. So there had to be something else that accounted for the rest of the mass of an atom. And in 1932, he discovered the neutron. And so now this kind of completes our, basic understanding of the atoms, where we have protons, we have neutrons, and we have electrons. Now, aside from that, when it comes down to kind of our modern view of the atom, this kind of combines all of the work from these scientists, as well as the work from Schrödinger and Heisenberg. Now, based on our modern view, the way that we kind of look at it is we have two main parts. We have the nucleus in the middle, and remember that's still a positively charged nucleus. And then we have this other space around it, which is known as the electron cloud. And so this is our current view of the atom, and we'll talk more about kind of why our current view changed a little bit later on in the year. But otherwise, that's it for today's video. I'll see you guys on the next one.